Now, why do we have to go to all these lengths? Traditionally, or long back, even now also, we do some load tests like this, which you can see in this image from the 1920s. This is how they tested a concrete pipe. Okay. So, you see here the concrete pipe that is being tested, and weight is applied. You keep on applying weight like sandbags here, sandbags until the load carrying capacity is reached. Okay. Then you know that it is safe, and if it broke, what would happen? The pipe gets crushed, and incidentally you see one person sitting inside. So, the story goes that this was the person who designed this pipe, and he was so confident, he said that I will sit inside. I do not know how many of the modern engineers would do this, but this person had the courage to do it. Anyway, that is the story, but this would be a traditional load control test, where you keep on adding load, you only want to know what is the maximum load the pipe in this case can take. Okay. However, we also want to know how this pipe or any material fails. When does it start failing? How does a crack propagate? So, we want to be able to get a response not only up to here, but also the remaining part. This is called softening, as opposed to hardening that we see in metals, where there is yield and then after yield the stress goes up, that is called hardening, and the opposite of that is softening, when you have a softening of this type. Okay. This is what is called a class 1 response. A class 2 response is where you have snapback because of some elastic component in the specimen or outside the specimen which is causing this. I will show you some examples of how a specimen can also give you class 2 type of response. Both these cases it happens because the material is softening, like concrete, rock, ceramics, these are materials which are softening materials. So, this is another way of looking at the difference between load control and what it can do, or displacement control. Suppose you have a specimen which is softening and it would give a load displacement curve like this. If you are going to do load control, the load is always trying to increase, the machine is increasing load. So, at this point the specimen cannot take more load and therefore it fails. But if you were to do a displacement control test, only displacement is increasing. So, at this point the displacement continues to increase and the reaction is the load, which is also measured, and you will get this complete curve. So, the objective always is to do a test such that you get some constantly increasing signal. So, the decision on which is the constantly increasing signal depends on your understanding of the test, and I will show you examples of how we can do different types of tests by this understanding. Suppose we want to do a compression test, say a cylinder or a prism, and we want to do a uniaxial compression test. All of us have seen, read that beyond a certain load the specimen just fails. Here you see graphs of the behavior even after the peak. This is lower strength concrete, medium strength concrete and high strength concrete. This is about 100 megapascal, this is say 40 and this is 20. You find that in all the cases the specimen has an elastic range, a nonlinear, reaches a peak and then continues to drop. This is the softening response that we want to capture. This is what is needed for nonlinear analysis of a reinforced concrete structure. If we do load control, we will not get anything beyond this. Okay. So, we need to capture this. However, we see that when this concrete is very brittle, the displacement does not change a lot, the axial strain does not change a lot. So, if we were going to use just the displacement or the axial strain for testing or the controlling, we may not get the response of high strength concrete. So, we have to look for something else that is always increasing, and the answer is the circumferential displacement. Okay. So, as concrete is compressed, it dilates, it expands, and this expansion is always increasing after the first cracking. So, if you see here, this is the same specimens, but here we are looking at circumferential strain, earlier we were looking at axial strain, and we find that without any drop, the specimen is always such that the circumferential strain is increasing. So, if we were going to control the test this way, then you will get a stable response, and this you can measure. It is not that when you do this you do not have the axial strain, which is important. You can measure this, but control, you can measure this and control with this. So, that is what we generally do. We can also switch control. For example, here we have this is the axial stress strain curve, this is the axial stress versus circumferential strain. What we find is initially the circumferential strain does not increase much. So, what you would do is start the test with axial control, and switch to circumferential later. Okay. At this point is where it is switched, because you want to start off the test such that you have some sensitive parameter. So, you start off the test with axial, or you can even do load control and then switch to the circumferential when you want it. So, this is the displacement versus time. Okay. So, what was done is it was decided that the axial strain would keep increasing at a certain rate, it reaches a certain point and then it switches to the circumferential strain, which then increases linearly. So, the control has been switched from a linear increase in axial strain until a certain point and then switch to the circumferential strain. So, a good control system should allow us to switch from one parameter to the other, and in our labs generally we would start off a test with load control and then switch to some strain control, could be axial then circumferential depending on the test. So, these are some tests by our group which shows the normal concrete, high strength concrete and fiber reinforced concrete behavior, and you can see that we have been able to capture the high strength concrete behavior even though there is a lot of snapback. I talked about snapback earlier. So, you see that there is, when we do very high strength concrete, the concrete is so brittle that there is no increase constantly of deformation. After some time the specimen just starts to break apart, but we still want to capture this, because for the structural analysis we need to know how this specimen or how this concrete is going to fail. And here we see also an advantage of understanding this. We have shown, for example, that the same concrete can change its post peak behavior significantly by adding fibers. So, this is the same concrete, the blue line is the same as the red line, but this has 80 kilogram of steel fibers, which whereas the red one does not. So, by measuring this we can also engineer the concrete, we can modify the concrete so that it does not behave in such a brittle manner, and for this we have to measure it, and the only way to measure it is to do a test of a specimen like this, where we have a chain that is placed around the specimen which is measuring the circumferential strain, and in addition we have to have measuring devices for the axial strain. We want the axial strain, but to get the axial strain we should also measure and control the circumferential strain. So, it is a very tricky test, but once you have a good system and somebody who is knowledgeable, we can easily get these type of responses and capture them. This is by one of our students, Steffi, where she is looking at the responses of different types of concrete. This is plain concrete, and these are fiber reinforced concretes, and she is looking at what is the effect of adding a little bit of fibers to see how the deformation changes. This is with 20 kg of fibers, this is with 30 kg of fibers, and this is 45 kg of fibers. Okay. So, this tells us how the post peak behavior or how the failure behavior of the specimen is changing or the concrete is changing as we add fibers. So, this type of test gives us that explanation. Okay. So, I talked about the possibility of controlling a test by using displacement. Sometimes we can combine also. For example, if this is the stress displacement curve, there are people who have combined axial stress and displacement to control by inventing a new parameter that is used for control. Okay. So, this is made into a curve like this, okay, or something like this, where this is the new control parameter x, which could be a combination of n times the load plus y times the displacement. Okay. So, a new parameter which does not have any physical meaning is invented to run the test such that this parameter given by this is always increasing. Okay. An example of this can be seen here. So, this is a tension test where we have a steel fiber reinforced concrete cylinder with a notch around it, and we are trying to do a tension test. We have glued it on to two plates and this is being pulled apart. So, there are two ways to capture the displacement of this. Either we put a transducer here, okay, which is telling us exactly how the crack is opening, and that is what is the control variable, then I would get this behavior, which is what I am looking for. Or what I do, I know that the load piston displacement is moving this way. I have to invent a set of parameters which show the axis this way. Okay. So, I control this variable x, which has a component of displacement and a component of load, and I tell the machine keep increasing this x in a certain way, and I will get a behavior that is now stable for the test to run, and then I can capture whatever response it is. Either I know exactly what is always going to increase and I measure that, or I look for a combination of parameters which is always going to increase, alright. So, these are things that again require a little bit of experience and trial and error to figure out how this should be done, and this is basically important when you have a behavior called snapback. Snapback is this, when the displacement decreases, and for many years until the 80s people never believed this was true. People thought this is impossible, this is just that some people are doing the test wrong and that is what is happening. But what all I am showing you are real test data where this is happening, and there is a Professor Surendra Shah who spent a lot of time on this, and you will hear him in another lecture of this course talking about other work that he has done. Another time when you can see snapback is when you use a very long specimen. Suppose you do a tension test on a very long specimen, say of concrete or rock. What we find is after a certain stress there will be one crack which will open. So, all the deformation is happening only at this crack, the rest is only elastic, okay. So, going back to the diagram I showed you of a spring plus a concrete specimen, that is what happening. This is the spring, okay, this is the spring, this is acting as an elastic spring, and this is the softening element. So, the larger the specimen, longer the specimen, more is the elastic part. So, if this was the response of the crack itself, this is the response of the crack itself. If I am measuring not here, but this whole thing, then I am adding on a elastic part which is this. So, I get snapback. There is a lot of snapback means what? Snapback means that energy is coming back from the elastic part when we are unloading. Okay. So, this part is in your load displacement is doing this, and this part is doing the softening. Okay. So, when you add, if this dominates you get this type of behavior, you get this type of behavior when you have a long elastic part, or in the same specimen if you are measuring very far away from the crack and including a lot of elastic part, then you have softening coming in and the test is unstable. So, that is why we have to figure out where we have to put the transducer, and in most tests nowadays we put a notch so that we know where the crack is going to start, and that is where we will put the transducer. So, this is an example again of snapback. Now, these are tests of one of our research scholars Sachin Paul, he will show you in a video of how these tests are done. So, this is textile reinforced concrete. So, it is a very ductile composite where you have in a cementitious mortar embedded glass fibers, and the possibility of the test that Sachin is running is that we can use a video extensometer. Until now we have talked about transducers, extensometers which are put on the specimen, but nowadays we have these sophisticated video extensometers which through a video camera is measuring tiny points on the specimen and calculating strains, and it is possible that you can use these strains to control the test. Okay. And in addition you could also have these axial extensometers which are looking at how the cracks are. So, these are some of the merits or more details of these video extensometers which are now available, so that without putting something on the specimen, but by looking at the image or a series of images or how the image is changing, you can figure out what the strains are and use it for control. And with something like that you could get a response which is shown here of stress versus strain in a textile reinforced panel like this, which is subjected to tension. And here you will see that there is an elastic part, then there are cracks, that is this part, and the cracks start opening more and more and you get this part. So, this will tell us the different zones of behavior for which he is doing his work. Okay. So, Sachin, you will see a video of Sachin explaining tests on TRC later on. As I told you, we do a lot of tests on notch specimen. The idea of using notch specimen, this is you will not see clearly what the specimen is, but basically it is a cylinder with a notch here and we are applying tension, because we want to know what is the stress crack opening behavior of this, what is often called the sigma W behavior. So, we put a notch because we know that the crack will only open there, we can then control it. So, you see here that this is the specimen very heavily instrumented, we have this system measuring the axial displacement, and then you have here these gauges measuring the crack opening. Okay. So, you can see we can apply load and see how the crack is opening and figure out what is the stress crack width behavior, and you can get a behavior like this. These are tests now on cores. Here you can, this is a better picture, you can see how the specimen, this is the notch, and you can see that there are 3 extensometers around the notch, and the average is plotted here as the crack mouth opening displacement. CMOD is the crack mouth opening displacement. So, we control the test such that the crack mouth opening displacement is always increasing, and you can see that something that is plain concrete gives a green curve. This green curve which almost shows no stress or no load carrying capacity after the first crack, it just fails. You are trying to open this and suddenly it breaks, but something with about 20 kg of fibers will have some load carrying capacity, 40 kg of fibers, and this is like an M70 concrete. Okay. So, even a very brittle concrete which has some fibers, when the crack opens, the cracks bridge, the cracks are bridged by the fibers and the crack does not open, and that is what you can see by doing this test. It is a very difficult test again, but it is possible. An even more complicated test and very challenging is to do the Brazilian splitting test. All of us would have heard about the splitting test, you would have studied about the splitting test, where we take a cylinder and we apply diametric compression and calculate the strength. Now, what we wanted to do is see if we can control this test such that there is no sudden failure. Anyone who has done this test knows that at a certain point the specimen just breaks, right, and you get 2 halves. But so the challenge was to see if we can run this test without this sudden failure, and we achieved it by putting 2 steel plates here. We know that the crack is going to run like this because that is how it has to fail. So, we put these 2 steel plates and put a clip gauge across this and try to control the test that way, and you see how the behavior is. So, this is what we are controlling, and these are different sizes of specimens. You see that you get this elastic behavior, then the crack starts and the crack is slowly opening, we are losing load carrying capacity and then it flattens out. So, we could show that even in this test you could obtain a stable behavior and then use this to understand how a crack is propagating under diametric compression. The same thing can be extended to unnotched beam tests. So, beam tests where you have that you use for the modulus of rupture, and also you want to see how this specimen breaks. And here you see a specimen that is instrumented with what we call a yoke, which is like a frame that is holding the extensometer so that we can get the displacement. So, it is very important that we get displacements right. Often what is done is there will be a dial gauge put here between the bottom of the specimen and the bottom of the testing machine, but this means that what you see as displacement will include many other displacements which are not just the displacement of the beam. For example, the crushing here, the displacement of these supports, all these will show up as displacement. So, what we do here is we have this frame which is clipped on to either side, and then we have this bar here, and on this bar the LVDT is attached and it is resting on something that is glued on to the concrete. So, we get the true displacement. Why would we do something like that? If we want to find out how the behavior of steel fiber reinforced concrete is. This is a beam without any fibers. Normally in a modulus of rupture test you get sudden failure, and if you control it right you get a stable curve, you get a post peak as this. This same post peak now with 15 kilograms of fibers becomes this, 25 kilograms, 35 kilograms and 45 kilograms of steel fibers. So, once you can do this test properly, we can assess how much of fibers should we get to get a certain stress after cracking, which we can use in design of pavements and other structures. The next step is to look at notched beams where there is a notch cut in the beam, and then we can put an extensometer across and we can do the measurement more easily. It is easier to get a stable test, and you see some examples of load deflection obtained this way or load crack opening obtained this way. And again you see the influence of adding fibers. This is the plain concrete, 20 kilograms of fibers and 40 kilograms of fibers, and this is a way of defining the flexural toughness. So, these are tests also which are done in closed loop servo hydraulic testing systems, and this is the behavior that you would get with a lot of tests. This is an M40 concrete with no fibers. This is from the thesis of Sujata Jose, who will also be showing you some of her tests. This is with 10 kilograms and going up to 45 kilograms of fibers, and you can see how the energy is increasing, how the load carrying capacity is increasing, and you can even see that in some cases the ultimate load carrying capacity or the maximum load carrying capacity is even much higher than the crack load carrying capacity because of the fibers bridging the crack. So, these are some things that you would not be able to do with load control. If you had done a load control test, you will not get anything beyond this point. The test will finish there because the specimen will suddenly break because the machine is only trying to increase the load. So, these are tests from Steffi Stephen, where she is doing these notch beam tests with a monotonic part. So, she loads the specimen up to 0.5 millimeters of crack opening, then she does a lot of cyclic tests. So, these are cyclic tests to see how fatigue is behaving. Then after about 2 million cycles she continues the test to see if the load carrying capacity has increased or decreased. Here you see for example that there is some residual damage there. Okay. So, these are tests that tell us how the fatigue behavior of the concrete would be, and in this case cracked fiber reinforced concrete. Now, these are some interesting tests of Prabha Mohandas, who is looking at uniaxial tensile behavior of pre-stressing strands. So, this is the image that I showed you right in the beginning. This is the frame, these are the columns, and this is the cross head. Okay. This is the cross head, this is the column, and this is the, these are the grips holding the strand. This is the strand that is being tested. This is gripped here and gripped here, and then we are trying to see what is the behavior. These are the parameters, and you have to grip it properly also. So, you see that you need some special grips, otherwise the strand starts to slip, and with this you will be able to get all this parts, all these aspects of the response which are important. This is a typical response that you would get. This is the stress strain behavior of the strand. You find a very nice elastic part as you would expect. That means that we are able to capture very nicely the elastic regime, then there is yield, then the load continues to increase until we have rupture of the first wire of the strand, second wire, third wire, and finally the whole strand ruptures. So, this to me is a beautiful response showing how the behavior of the strand is as you increase the load or increase the strain. Okay. And again, for this we need a testing machine which can apply displacement at the same rate, does not change its displacement rate or stop applying load when there is a sudden change. You see here that here a wire has broken, but still the machine is able to continue the test without stopping or releasing the load completely. An extension of Prabha's work was to look at the pull out of pre-stressing strands from concrete. So, this is the same machine, but here instead of just the strand, now what she is doing is holding a small frame here which is shown here. So, here is the frame which is attached here, okay, in the testing machine, and we have a block of concrete. Inside this concrete there is a strand, you can see the strand here projecting. The strand is held at the bottom in this wedge and the frame is held at the top wedge, and this whole thing is pulled such that slowly the strand is being pulled out of the concrete block. Okay. So, the idea is to understand that behavior and see when and how it pulls out. Okay. So, this also means that we need a system that is having a large enough space that you can put this and having enough load and having a displacement stability to do this test well. Typical response would be like this. Here we are seeing the bond stress, the nominal bond stress load divided by the embedded length and the slip, and here she has the relation between the stress and the slip, the live end slip, live end is what is being loaded, and the free end which is at the other end is this type of response. So, based on this she calculates parameters, and there will be a video where Prabha will explain how she does these tests as well. So, I will close with this. Thank you very much. Have fun breaking things in closed loop. Thank you.